Hello and welcome back to Haybridge Maths Department, Year 2 Pure, where we're looking at Chapter 3 and we are looking at series. Okay, so this is the second part of a video we're doing on modelling with series. The first one should be available already. You should have watched that. If you haven't, go back and watch that model first. Make notes on that. Now, at the end of the last video, I gave you an example where I wanted you to take notes. What I'd like you to do, first of all, is look back at those notes and then have a go at this example that you can see here. When you have finished that example, then restart the video and I will go through it here. Okay, so if you haven't done so already, pause the video now. And I am going to go through this right this minute. So we have these perspectives, and each time I drill down 50 meters, it's getting more and more expensive. The deeper you go, the more expensive it is to drill even further. So let's have a look. What we want in part A is the total cost of drilling to show that it is equal to 11,300 when you go down 500 meters. So what we're looking at here is if you're going down 500 meters and we're talking about lots of 50, then we're looking at 10 goes down. So we're looking at the sum of the first 10 terms. And we're looking at 500 because that was the first one. The second one is 640 plus 720 plus until you've got 10 terms there. And we have in this is A is equal to 500, D is equal to 140, and n is equal to 10. So you've got 10 terms, it's going up by 140 each time, and the first term is 500. So if you remember, the sum of the first n terms of an arithmetic series is n over 2, 2a plus n minus 1d. And what we have here is a simple substitution exercise now. So we're looking at the first sum of the first 10 terms, and n over 2, that's going to be 5. 2a is going to be 1,000. N minus 1, that's going to be 9. And we're timesing it by 140. What you're going to do now, plug it all into your calculator, and hopefully you will end up with £11,300. Okay, so give yourself a big tick if you got that right. If you didn't, have a look at what I did, see if you agree, and let's have a look at part B, where we're saying we've got a budget of £76,000. What I want to be able to do is see how far I can drill, how deep can I go with £76,000? How far into the surface, into the earth, how far below the surface can I go? So this time we're going to use the sum formula again. We're going to use this formula here once again, but we're going to have to do some rearranging because we know that 76,000 is going to be, well, we don't know what n is equal to. So we've got n over 2. A doesn't change. It's still, we're going down we're going down in the first 50 meters, it's going to cost us 500. So 2a is still 1,000. That's not changed. And the D hasn't changed. It's still going to cost us 140 quid each time we go a little bit further, or we go 50 meters further. So it's going to cost us 140 quid more I should say. We have to be very careful about that. It's not going to cost us 140 quid to go down 50 meters each time. It's costing us £140 more. So we end up with this equation here. It needs a bit of rearranging to get n out, but I can see I've got an n here and an n here. Those two are going to combine. We're going to get a quadratic out of it. So we're going to need to rearrange so that we've got the quadratic equal to 0. But if you've got that quadratic equal to 0, you have a calculator, but we'll solve that with a quadratic solver. You don't even have to plunk it into the formula. So you can just rearrange. You don't have to do anything really to the coefficients to make it easier if you don't want to. Just stick them into the solver and your answer will come out. So if we do that, then we've got to expand. Let's get that 2 over there because nobody likes that 2. So we'll do 152,000 here. We'll keep that n there now, and we'll expand out this bracket here. And simplify all in here. So we'll do 140n, take away 140, 1,000 take away 140 is 860 plus 140n. What we'll do now, expand out the brackets so that you get 152,000 equals 860n plus 140n squared. Take the 152,000 over to the other side, so you've got 140n squared plus 860n minus 152,000 equal to 0. Right, now we don't, as I said before, we don't need to do anything more than just reaching for our calculators, sticking it in, and you should get an answer out, one that's negative. Well, you can't have a negative n, discard that immediately, and if I remember correctly, you get a decimal answer. You get a 30 point something, if I remember correctly. Now, the thing is, if I've got a budget of 76 grand, I can't go over that budget. So I might have to say I'll go up to 30. All I can say is that n equals 30. We can't go, if it's a decimal answer like 30.2, 30.7, well, we can't go above the budget. So we're just going to have to round down, even if it's like 30.7, we'll round down to 30. But that's not what the final answer is. If you've got that, you haven't done the question completely. It's got n is equal to 30, but we've got to remember that it asks for the distance, the question does. So the question asks for the distance, and you're doing 30 lots of 50 meters. If you look back at the question, it says that it's 50 meters ago. So you've got 30 lots of these 50 meters. So the distance is in fact 30 times by 50, which is 1,500 meters. There you go. Okay, so if you've got that, well done. I don't think it's that easy a question, especially part B, but there you go. If you want to make sure that you've got all this into your notes, please do so now. And then we're going to have a look at a geometric series here. Well, it's not going to be a series, it's going to be a geometric sequence. So let's have a look at this now. So we've got a piece of A4 paper, and we're doing that trick where you keep on folding it and see how far you can go. The thickness of the paper is 0.5 millimeters. So that's where it starts off with. We start off with a thickness of 0.5. We fold it, so we give one fold, so it's like your second term. You're going to have 0.5, and if it's folded, it's going to be on top of each other. So you're going to have 2 lots of 0.5. So we're going to go 0.5, then 2 lots of 0.5. And then if you've got the two bits on top of each other, fold it again, and those two bits are going to go on top of two other bits now. So you're going to have 0.5 times 2 squared. You're going to have 4 bits of a paper. And you're going to carry on like this. Each time you're folding, then you're going to have double the number of pieces of paper as you had before, and each one is going to be 0.5 thick. So you've got to times it by 0.5. So after 4 folds, so that's 5 terms. If you think about this one here, this is before any folds. So you're looking for 5 terms. So here we've got A equals 0.5, R equals 2, and N equals 5. It's a 5th term. So the 5th term is going to be 0.5 times 2 to the n minus 1, which is going to be, well, 2 to the 4 is 16. So you've got 8 millimeters. Okay. I think that's actually easier, as long as you get around the head that the first go isn't the first fold, it's just the original thickness of the paper. As long as you've got that, maybe I'm wrong, but this example is easier than the example with the arithmetic series. Okay, have you ever tried folding a piece of paper 20 times? It can't be done. But let's have a look at how thick the paper would be if we did fold it 20 times. So on this occasion, we're looking at U21. This is part B, by the way. And then part B, you want U21, which is going to be 0.5 times 2 to the power of 20. And if you do that, apparently you get 524,288 millimeters. So yeah, you're not going to be able to do that. It's ludicrous to suggest that you would. So state one reason why this model might be unrealistic. I've said the answer already, but you need to write something down. As the paper cannot be folded that much. Okay, so make sure you've got this into your notes, and then what I want you to do is I want you to make sure you've got all this into your notes here, and then have a go at this example here. Okay, hopefully you've had a go at this. This is, I'd like to say, a genuine example, in that 7% is what the stock market has historically done. So over the last, I don't know, quite a long period of time, on average, the stock market in the FTSE 100, I think, has increased by 7% each year. So if I stick a certain amount in now, how long will it be before that doubles? If I'm sticking £1,000, how long does it take to get to £2,000? If I stick in 100 grand, how long does it take to get to 200 grand? Right, so it doesn't matter what our initial value is, our principal value, if we just call that A. After 1 year, you would times it by 1.07. After 2 years, you'd times it by 1.07 to the power of 2, to the power of 3, to the power of 4. So you've got another geometric that is going to be going here. So just be careful with this again, because you're going to go to, it's always going to be A times 1.07 times to the power of n minus 1. When is that is going to be 2a? Well, if you do that, then you're going to be, just looking at this, sorry, 1.07 to the n minus, excuse me, 1.07 to the n minus 1. Right, what you've got is these a's will cancel. The 1 will divide 3 by the other, and you get 2. What we've got now is a log equation but needs solving. So you've got n minus 1 log 1.07 equals log 2. Divide through and add on, and you get n equals 11.2 years. That's if you count the first year as a point from when you actually stick the money in. So it depends where you define that first year. Is the first year starting when you put the money in, or when does it double? But when does it go up by 7%? But the point is here, we have, so you could have an answer, I should say, you could have an answer of 10.2, not have n minus 1. It's something that when I was doing this, I was working through, and I think in an exam situation, they'd have to kind of be a bit more specific about when the first year ends, or do you start it from year 1 at the start or at the end of that first year, if that makes sense. Now, there is a point about this. I've mumbled through that point there. I think I should say in an exam, I think they'd accept 10.2 or 11.2, or they would word the question a bit more specifically than I have done there. Now, there is a serious point to this beyond this, and that's the power of compounding. If you've got some money and you want to invest it, then I guess the advice from this is start doing it as early as you possibly can, because compounding will enable your money to grow, and the longer you leave it, therefore, the more money you'll have. So any cash that you've got now, save it in your pocket money. Don't spend it on anything other than a nice ISA, a stocks and shares ISA. Put it away and don't spend it on anything frivolous whatsoever. And then in a few years' time, you'll have lots and lots of money and you'll be rich. Okay, now there is one final example that I wanted to talk to you about, and it's something that I've thought long and hard about. We are living in a time of crisis. We are living through COVID-19 at the moment and the effects of that. Now, we are also looking at modelling here with geometrics. And a lot of the modelling that has taken place over the last few months about COVID-19 has used geometric sequences. It has occurred everywhere. And this fella here is Professor Neil Ferguson. He was the guy who used modelling back in March 2020, and he looked at the government's idea that we could have herd immunity, and that if the virus could just pass through the community and we would just get over it and it would be no worse than a dose of flu. And he looked at the numbers and he used a more sophisticated model than just a geometric series. It's more complicated than just a simple geometric, but at the heart of it is a geometric sequence. And he looked at it and predicted that within a few weeks there would be 500,000 people dead within this country from COVID-19. And it was his modelling and his group's modelling at Imperial that said we need to go into lockdown. So the government acted on the advice of Neil Ferguson, and the government and the country into lockdown. Since then, Neil Ferguson has come out and said that not only should we have gone into lockdown at that point, we would have been better off going into lockdown earlier, would have gone in a week earlier. Half the number of people that have died from COVID-19, um, half the number would have survived, or half the number would have died, depending which way you want to look about it. I'm not going to do an example with numbers because I think it would be crass. I think, given we're talking about people dying, and this is really what has happened, I don't want to do an actual example. But what I did want to make you fully aware was what we are doing here has major relevance to what has been happening this time with COVID-19 and everything. So this is very real, practical applications that has affected us greatly over the last few months. Okay, so what I would like you to do now is I would like you to have a go at exercise 3I. So stop the video. Well, I'm going to stop it in a second. And could you have a go at exercise 3I? Thank you.